Off we go. Okay, so randomness is just the idea of like telling the computer to flip a coin, right? Telling the computer to roll a die. We can make that happen, and that lets us like make simulations happen. It lets us see like what are all the different ways that could have been like what are all the different outcomes that could happen just due to random chance. You can let the computer simulate that, and we can see how likely a certain event might occur. So that's really cool. This is chapter 9 stuff. Please read that chapter 9. And the very first thing I want to show you is from the NumPy library. It is a function called np.random.choice. It's really called choice, but it's part of the NumPy library. It's in the random module, and it is called make a choice for me, please. And what you put within the parentheses, the choice function, all it does is it takes a sequence, like an array, of options, and it will pick one option for you. So like you put in all the different things you want to have for potentially for dinner tonight, you can press enter and it will pick randomly one of those things that you provide there. So it's np.random.choice. You can go pretty far with just that. So let me show that to you. There's also, of course, documentation on it. Let's go to that as well. Random.choice. Surely it was in the sidebar as well, but here it is. Yeah, here it is. np.random.choice. All it is it's a function that takes, a function that takes an array of things, and then it will give you one element of that array when you run it that was chosen randomly. So if you run it again, we'll probably choose a different one for you. You can also ask it to give you a bunch of things from that with or without what's called replacement, and then we'll get into that later. But let's just run it by itself with a sequence of potential options to choose from. We can decide what I eat for dinner tonight. So let's see here. You say np.random.choice, and then you give an array of a bunch of things that you want to choose from, and it will choose one of them randomly for you. So let's see, I could have breakfast for dinner. I could have, I like to make a calzone for dinner sometimes. I like to make like orange chicken from Costco or Trader Joe's for dinner. Let's say that those are my three options. I can make an array of that, and I can ask np.random.choice to choose one for me just completely randomly. Hit Shift-Enter. It's like, all right, you're going to make a calzone for dinner tonight. And so it just randomly chose that element for me, and it gave it back. You can run it again. It randomly again chose calzone for me. But if you run it enough times, it will give you back something different. And I guess I'm having orange chicken tonight. Okay, so that's np.random.choice. It's very simple, but it goes very far. Does that make sense? You just give it a sequence. It will pick an element of that sequence for you and spit it back out randomly. So it's different every time. The other way you can use np.random.choice is to get a bunch of things. Pick 3 elements randomly from that array and give it back to you. Give those 3 elements back to you that were picked randomly as another array. So let me show that to you. So if you give a second argument to np.random.choice, that's you asking it to pick randomly 5 times now from that sequence. So now it's given me back an array of size 5, because that's what I asked for, right? 5 things. Randomly pick 5 times from the sequence, and then give me back all those random things that you picked. So this was the random things that it picked in that order. All right? And you better believe that if I run it again, I get a different 5 things still, but in a different random order. So that's pretty neat, right? And we can use this to simulate and like flip coins, for example. Like, all right, who's paying for dinner tonight? Let's flip a coin. We can ask Jupyter to do that. Okay. So are there any questions about np.random.choice before I just show you examples for it? Pretty simple, right? So let's flip a coin. I think that's really what I want to do. So what is a coin but an array of heads and tails, right? Heads and tails. That's all it means to be a coin. It's like one of those 2 things. So let's call that the array coin. And then I'll say np.random.choice from coin. It'll give me a random element. It picked tails. Okay? If you run it again, it'll pick something else. You can have np.random.choice flip randomly as many coins as you like right in a row, right? You can say, hey, flip 42 coins by picking randomly from this coin array 42 times. So this is 42 completely random coin flips, and it went tails, heads, tails, all the way down to heads, heads. That's pretty neat. Okay? So that's np.random.choice. Very simple, right? But very powerful. It'll let us do simulations, like we've just flipped a bunch of coins. Maybe you won some money, depending on what you just did. So that's neat. That's cool. That's np.random.choice. And now I just want to use that in some cool ways, and so let's build up some knowledge to get there. All right? So I want to talk about comparisons. Again, we've seen this before, but I just want to go back to it. It's a little weird, but it's important. So you can ask Python, right, to go and tell me if is one thing less than another thing, is one thing greater than another thing. Let's see what is what, okay? And the results you get back are true and false instead of yes and no in Python land. So you can ask Python, hey, is 2 less than 3? Just by typing, hey, is 2 less than 3? And it will say yes by giving back true, right? It will say no by giving back something called false with a capital F, okay? And if you're asking for like less than or something less than or equal to something else, it's really hard to type this symbol in a computer. And so they've just chosen to turn that into a less than sign and then an equals to sign, or a greater than sign and then an equals to sign to mean greater than or equal to. And Python will do the math and like figure out, hey, is this thing equal, greater than or equal to, or whatever, and say yes or no by saying true or false. So you can just ask Python, hey, is 1 less than 2? And it's like, yes, it is. So it says true. It says true to give that back to you. And then false means no. False means no. So like, is 42 greater than or equal to, I don't know, 55? No, it's not. False. Okay, so that's comparisons. We do have to be careful when we're checking for equality, because equality checks are double equals instead of a single equals, because that one's already overloaded, right? If you were to say x equals 42, that's you setting a variable, right? That's you setting a variable. That won't work. If you want to check for equality, hey, is x equal to the value 42? We've chosen to make that a double equals. So there's a huge, huge difference between the first thing and the second thing. I hope you see. So checking for equality, hey, is this true, or is this actually equal to, are the two values equal? I don't want to set anything. I just want to know if they're equal. You tell me. That's double equals. So hey, is 2 equal to 3? 2 equals 3. No, it's not. False. Okay? So yeah, that's what I wanted to say. There's also not equals to. It's an exclamation point and an equal sign. So hey, is 3 not equal to 2? Yes. Is 2 not equal to 2? No, it is equal. That one's a little weird to wrap your mind around, I know. So there's that. But those are comparisons. And where I'm going with this is you can compare a bunch of arrays to things. So I want to show that too. But do comparisons make enough sense? Coming back to us. Yeah, just remember the double equals for checking for equality. That's important. But just like you can have an array and mess with all the elements of it with math, let's say I have the array 1, 2, 3, I can multiply all that by 5, right, to make the array 5, 10, 15. I could also do comparisons on the entire array at once. So I can say, here's my 42 coin flips. I can do that. And then I can ask, hey, how many of these, or which of these were heads? I can do this check. I can check the equality of the entire array with heads, and then it will go through that entire random array and say true for each piece where it was heads and false where it wasn't, because it's going to apply that operation. Hey, was it equal to heads for each element of this array? That's what it's about to do. It will be a random array again, so it might not be tails first. It might, but if it was going to do this on this exact array, it would say false. False, true, false, false. False, then true again. It's just going to check. And so it's going to give me back a bunch of falses and trues because it went into all of these things, this random array. It looks like it was tails the first time because it was false, tails the second time because it was false. But it was heads the third time because equals heads gave back true. It gave that, and it worked for every element of that array. So this, we turned this like flip every coin and give you back heads and tails strings into trues and falses. Does that make sense? So you can check for equality or like do less than and do whatever you want with an entire array by putting a comparison with one value next to an entire array. We'll apply that comparison to each element of that array. All right, that's pretty neat. So where I'm going with this is it would be nice to flip 42 coins and figure out like how many were heads, like count how many trues are there right now. Okay, and the way we get that is with a weird function called np.countNonZero. It will give you back the number of non-zero elements in an array. So like you give it an np.countNonZero this array, There's a few of them that are not 0. We count how many weren't 0, all right? And for very odd reasons in Python that I don't want to get into really, it's like true is a 1 and false is a 0 to computers. So it's like 1 binary on and off. So true is a 1, false is a 0. So counting non-zero on an array of Boolean values of trues and falses, results of comparisons, it gives you back how many trues there were, because false means 0 to Python. Which also implies that you can do math with false and true. You'd be like, hey, what's true plus false plus true? You better believe this answer is going to be 2, right? Isn't that weird? So that's why we have that. But that ability now gives us this. We can take this, hey, let's build it up together. This is me getting a bunch of random coin flips, 42 of them. This is me checking how many, which of those were heads, true or false, right? Which of these are heads, false and true. And then I can ask how many were heads by counting the trues. I can say np.countNonZero. This whole result of trues and falses, and then it will count how many trues there were. And apparently this time, there were only 16 heads out of all of them. I'll run it again. Now there were 26. It's random. It's not exactly, you expect to see, 21 heads, but it's not gonna, it's gonna fluctuate, right? It's random. So this line right here, line below, counts how many heads there were in the 42 random coin flips. Isn't that weird and cool? Are there any questions about this line and how we got to this? So there's a whole sequence of ideas that we just chained up together. You see it? See the progression? It's pretty neat. Yeah, you run it again. Another random coin flip. We got 26 again randomly. Crazy. Now 15. Now 21. That's the expected number. We'll see that the most amount of times, but still, we'll get other amounts some other times. Now it's 19. Now it's 25 heads in the 42 random coin flips that Python flipped in the blink of an eye. That's pretty fun. So yeah, that's just a bunch of, that's random.choice and comparisons, and counting non-zero gives back how many trues there were if you had an array of trues and falses. All right, it's a lot of ideas together. Do you see it? Questions about that before I go to something else? All right, so the next thing I want to do is kind of go back to comparisons, and I want to teach you more about comparisons. I want to show you a piece of syntax in Python that's going to be very useful to us. It's called a conditional statement that lets us do like one thing or another. It lets us branch off in our code. So I want to show that to you. And the way that you branch off is by a yes or no answer. Do I go left or do I go right? Is by a comparison usually. So this is a conditional. There's a bunch of different kinds. It's like the simplest kind is this one, just an if. Then there's an if-else. And then there's an if-elif, maybe potentially a lot of elifs, else. We'll get to that, all right? But these are statements in Python that you can ask to run code for you when a condition is true, and only when a condition is true. And then you can also give something to run when it's false as well. So a bunch of options. I just spilled water on my tablet. All right. Let's talk about it. So this is the simplest one. Let's start with it. It's called an if statement. And what it does is it runs what's inside of it. You do the colon again. You say if some condition that's like, I don't know, 2 equals 2. Some sort of condition that results in true or false. It doesn't have to be something that's always true or always false. It's maybe something that depends on a variable that you got from the user, something like that. And then you have a colon, and then you indent, and that's called, just like it was for functions, this is the body of the if statement. We say, this is just syntax at this point. This is the body of the if. And how this code works is it checks the condition, and if that condition happened to be true, like if you gave 2 equals 2, it will run what's indented, what's in that true branch for you. It will run all that code, whatever you put there, it'll run it for you. And if the condition was false, like you checked, hey, was 2 equal to 3 or something, it would skip it. It just wouldn't run any of the code that was inside at all. So it would skip all that. So if statements, they run their body if their condition is true, and they do absolutely nothing otherwise. All right? So that's an if statement. Let me show you an example of that. So this is an idea called conditionals. There's a bunch of different ways to do it, but the simplest one is just an if by itself. Conditionals. So let me make a function that uses an if statement. That will be fun. Let's make a function that tells me like what the sign of a number is, like if a number is negative or not. It's a function called like sign. If you say negative 42, like the sign should be negative. But if you say positive 42, the sign of that value 42 is positive, right? So let's make a function called sign, and it takes some value, call it x, and we'll print out negative if the sign of that number is negative, right? So if that x value that I got is less than 0, what do I want to do? I'll give back the idea of negative. So this is functions plus if, but we gotta make it work. All right, we gotta remember. So this is the sign function. Now when I give negative 42 to the sign function, it's gonna run with x set to negative 42. So it'll run this code and we'll ask, hey, is negative 42 less than 0? It is. That will be true, right? And so it will hit this line and return back negative, the string negative. So I do see negative given back to me there. Does that make sense? What's going on there? It was checking. We got the negative 42 as x for this function call, and it gave back the answer negative because that's what we said we wanted to happen inside the body of that if statement. All right. And if this is false, it just doesn't run. Just doesn't run this body here. So it's not going to do anything at all if we give some number that's not negative. So if I say, hey, what's the sign of 5? X will be 5 for this call. Is 5 less than 0? No. So it'll just skip out on this whole if, and it won't do anything at all. I just press Shift Enter. I got no answer. Does that make sense? It just skipped. We never got to a return statement, so we didn't give anything back. Yet, at least. Does that make sense? You see it? It just does nothing if it's false, if that condition was false. Sometimes, though, you do want to do something if it's false. You want to do like one thing or another. Hey, if it's true, do this. Otherwise, do this. Like you can read, like the other option is otherwise. And that brings us to the idea of an if-else statement. So an if-else lets us do one thing if a condition is true and then like have a fallback. If it's not true, do something else. Okay? So if-else statements, they look like this. You say if condition, colon, you indent, you give all the code you want to run if the condition was true. And then you also say else colon, and then you indent and give all the things you want to have happen if the condition was false. And we call those branches because like what your code is doing is like it's asking the question, the condition, and it's going down one branch or another, right? This is the true branch, this is the false branch. True stuff, false stuff. Does that kind of make sense? It's going to pick one of the sides, and it's going to run down one of those. Those sides are called branches because it looks like the branches of a tree, kind of. True branch. This is the false branch. So it'll only ever run one or the other, of course. I hope you kind of get it. That's what's going on. So if the condition was like, hey, is 2 equal to 2 again, it would run this code. But if the condition was 2 equal to 3, it would run this code. It would hit the false branch. Okay? That's how it would work. It goes down one side or another side. That's how it works. So let me show that to you. If else gives you another option. So let me update this function, and I'll keep the old version here so you can see it. So I'll say, all right, the sign of a number can be also positive, right, or non-negative. So let's say, all right, if x wasn't less than 0, let's have an else. Let's be like else colon. What do we want to say if this was false? That means it wasn't negative. That means it's either 0 or positive, that x value. So we can say the fancy mathematical word for that is non-negative. Because we're not sure if it's positive or 0. We can have another check, but we still need to do that. So this is called the true branch. If the condition gives back true, we run that code. This is called the false branch. If the condition was not true, if this evaluated to false, then we give back non-negative. And so now I've got a side to go down no matter what. Either way, one way or another, I've got this case, I've got the fallback case for else. You read that as like otherwise. Otherwise, do that. So I can, again, ask for what's the sign of negative 42. I still get negative, right? Because it said x is now, we call it x is negative 42. Is negative 42 less than 0? Yes. So we return negative. We went down that branch. We skipped the other one. It's always one or the other. But now I can also say, hey, what's the sign of 5? Non-negative. Because x becomes 5 for this call, right? X becomes 5 for this call. And then we ask, hey, is 5 less than 0? No, 5 is not less than 0. And so it hits the else. It runs this code. Everything in the false branch, that was our fallback case. Okay? That was our fallback case, and it's happy. Okay? So that's us running one thing or another thing. Does that make enough sense? Questions about that? It's very powerful. Sometimes you want to try a bunch of cases. You want to do like, all right, otherwise, all right, if the first thing doesn't work, try this one. All right, if that one doesn't work, try this one. If that one doesn't work, try this one. And then like have a fallback case still. That's called an if else. All right. So this is, you can read elif as like else if, like otherwise. It's like else and if kind of combined together because it has another condition here. All right. So what elif does is it kind of goes in the middle of your if else and it has some other options. So it's always going to check, the way that Python runs this is it's always going to check your conditions in order of priority. Like it'll try to do the first one and the second one if that one fails, but it's always going to want to do this one first. Like it's going to run one of these bodies, your if elif else. It's going to run one of these bodies. It's going to run the first one that works, the first one that's happy, that gives back true. So this is kind of what's going to happen when we run this code. This it's first going to check the condition 1, and that one's got our highest priority. Highest priority. And so if this one's true, it will run this code right here and skip out on everybody else. That was the first one that worked. It's happy. Okay. If that one fails, it will go on to try the rest, and then it will try this one next. This one has the next highest priority, and it's going to ask, all right, otherwise, read elif as like, it's really short for else if together, but read it as otherwise, like otherwise maybe condition 2 works. That one's the next highest priority. Next highest priority. Then it'll try to do that condition. Maybe it wasn't negative, but maybe it's equal to 0. I don't know, maybe that's the second option. So we can say, we can give it something to do if some other condition is true, that's some fallback condition. Like, all right, try this one if the first one didn't work. And if that one's true, it runs this one. And that's the only one. It doesn't go to the else. So like it chooses one path to go down, the first one that works. That's how if elif else works. And then you could totally have a bunch more elifs. You'd be like, all right, otherwise condition 3, otherwise condition 4, whatever you want. As many as you need can go here in some priority order that you decide as the programmer. So more elifs can go here. All the way down to, you can skip the else, but you can still have an else as well. So the else is just like your fallback case still, just like the other one for a normal if else. That one is like, if nothing works out, if everything goes wrong, then we still have something that we could try and some code to run still. It's our fallback, our give up case. So if none of the conditions above work out, we'll run our false branch. But you don't have to have an else case. You can just be like, all right, if nothing else, if none of these work out, don't do anything at all. Skip it all. So you can mix and match kind of. But these are the 3 main patterns of a way of making an if else usually. You can have an empty body if you want sometimes. But yeah, it's elif is short for else if, but I want you to read it as otherwise, and it'll just go and find the first condition that's true, and it'll run that body. So like if this one's true, it runs this one and it gives up on everybody else. If that one's not true, then it tries this one. And if it's true, it goes and runs this body and gives up on the other one. If none of those first 2 conditions were true, and none of the other ones too, if you add more, it'll hit the else. That's how that one's going to work. Does that make enough sense? That's how it's going to deal with and do its stuff. And I think we can finally make a perfect sign function now, because the options for the sign of a number is like, is it negative, is it positive, or is it 0, right? Let's do those 3 options with an if elif else, okay? So one last version of the sign function. We'll do it this way. We'll be like, all right, hey, if x is less than 0, the thing that I was given, if it's less than 0, yeah, it's negative, return that. Otherwise, elif, maybe it was positive. If x was greater than 0, then give back positive. That's another option. That's an alternative. Otherwise, if maybe this is true, do this one instead. See that? There is a priority going on, but a number can't be both negative and positive at the same time. So these orders don't matter for less than and greater than checks, but sometimes it does matter. And then if none of those are true, if it wasn't less than 0 and it wasn't greater than 0 and it was a whole number, it must have been equal to 0. Yes? So that means you can say 0, you can say neither, whatever you want. But do you see how if you ever get to this else, we've tried the other options and it must be 0. The only other option is x is equal to 0. So you could have had an elif and just been like, elif x was equal to 0. But that's kind of redundant. You can just be like, you can let that be the fallback case because that's the only other option for whole numbers, right? Else, return neither. And so now I've got an option for no matter what. And I think that's a cleaner version of the sign function because not a lot of us day-to-day say non-negative, but we say positive and negative, don't we? So, all right, this version of the sign function, it works for positive numbers. I say sine of 42. X is 42. It tries this one first, right? Hey, is 42 less than 0? No. Then it tries this next one. Otherwise, okay, maybe this one works. Is 42 greater than 0? Yes. So it returns positive, and that was the one side it chose to go down, and that's the end of the function. See that? It's the end of the if else. It's the end of the function too, and it's happy. It picked that one side to go down. It's never going to like print both positive and neither. This way, just it picks one body, and it sticks to that one. All right? So you can ask for the sine of negative 42. That will hit this one, right? Negative 42 is less than 0, so it will hit this branch. It'll go down just that one. It only picks one to go down, okay? And then finally, if I say 0 here, we hit our fallback else case. It'll go to neither, and I hope you see why. It's like, all right, is 0 less than 0? No, not strictly. Is 0 greater than 0? Strictly greater than 0? Absolutely not. So, all right, this is the only other option, so it runs that one. See it? Any questions about this new and improved final version of the sign function? Isn't that cool? All right. So yeah, you can do, I don't think you're going to care much about this, but like you don't need to make a sign function too often in your life. But let's make an example of a function or like a conditional that like is near and dear to your heart. Let's do a grade checking conditional. Like let's write some code to like take a percentage score from somebody and turn it into like A, B, C, D, and F, because that's like somebody in Canvas programmed that to estimate your grade, right? That's actual code that's running somewhere. It's less theoretical than a sign function. So let's be like, somebody gives you a grade equals something. We got that from somebody maybe. And then let's spit back out, like if that's a percentage like 90 or 85 or something, let's spit out if it was an A, B, C, D, or an F grade. Yeah, let's do that. So here's how I would think about this. Let's just do A first, right? So if your grade percentage was bigger than or equal to 90, then it's an A, right? Maybe it's extra credit, but like that's for sure an A, yeah? 90 or above, at least in my class, that's an A grade. So I'm not in a function, so I'm just going to call the print function to print out something for me. So I'll print the A character, okay? Otherwise, right, maybe the grade wasn't bigger than or equal to 90. If it wasn't bigger than or equal to 90, I will get to this next case, and I know for sure because I didn't hit this one that it must be the opposite of this, right? What does it mean to be the opposite of bigger than or equal to 90? It must be strictly smaller than 90. So if I get to one of these next conditionals, then I know for sure that the grade can be at most 89.99999, right? It cannot be 90 because it would have run this code if it was bigger than or equal to 90. So I know here, if I get to here, it must be smaller than 90, right? Because that's the opposite. So if it's smaller than 90, maybe it's bigger than or equal to 80. Yeah, and then I'll print B, right? Do you see how just by virtue of getting here, if we get here, we know the first condition failed. So grade must be less than 90 because that's the opposite of greater than or equal to. Does that make sense? So if I'm within this one and this one works, that means the grade must have been between 80 and strictly smaller than 90 if I were to get to here. Does that make sense to us? If I run that one, that must be what's happening. And that kind of logic goes on all day long. I can keep having a bunch more LFs. Otherwise, all right, if that wasn't true, then I know the grade must have been smaller than 80, because that's the only way to make that false, right? So, okay, if it's smaller than 80, maybe it's bigger than or equal to 70, right? Do you see how this is correctly going to check for, like, was it between 70 and 79.999? If we get to here, we know that the other two checks failed, which means it must be smaller than 80. So it's at most 79.999. So if it's between that and 70, now we can check for if it's a C. Yeah? And we can do the same for D and the same for F. So otherwise, all right, if that wasn't true, try, was it bigger than or equal to 60? And that is going to, you see, by virtue of getting there, we know it's less than 70, so this is a D. And then you can either do it this way or another way. You can still stick to an LF. You don't have to have an L. So you can be like, all right, otherwise, if none of that's true and grade is less than 60, then it's an F. And you can do that. You don't have to do it on it. You can have the last one be LF. It does not have to be an else. And it will run, it will be an F if all these fail, right? If that one fails, that one fails, that one fails, that one fails. This is kind of the only option left, right? It must have been smaller than 60, so you can print F. And so because this is kind of the opposite of the one above, we only got here to this less than 60 check. If we know that this one failed, then this is kind of redundant, right? I could just call this else. Like if that's not true, then it must be an F. Does that make sense, that kind of condition, that trial and error process? This one has highest priority, that's next highest priority. This order does matter. So if you imagine I change these around, something might go wrong. But let me just show you it working and we'll go from there. It's like, hey, was the grade's 95 or 95.5, doesn't matter. You see how this code is going to print A, because grade is 95.5. This one will be true, and all these guys are connected. A big long chain of if, elif, 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 else. It's only ever going to run the first one that works. Okay, it's only going down one of these bodies. It's going to pick one, and it picked the first one because this is true, right? That was the highest priority condition. That one will be true. Do the same for 85.5 or just like 89.999. You see what's going to happen. It is B because this is not true, right? For if grade is 89.999, then it is not greater than or equal to 90. So let's try the next one. Oh, but it is greater than or equal to 80. So that one hits, and we know that that means it's within the B range, right? Same for like 75.5. I think you get the idea. Like this one fails for 75.5. So does this one. So it tries this one, and that's the first one that works. And so that's the code that goes down and runs. See that? So that is pretty neat. That's the idea. And yeah, are there any questions about that? Does that make enough sense? What's happening with that code? How it's running? It'll also work for D and F, that's for sure. It is, you do have to be a little careful because this order really matters. It really, really matters. You can't have the D case first and do it this way. Watch. I would have to change this one into an if, right? And this one to an elif. Do you see how, if the grade was even like 95, this code right here is going to print D even though it should have printed A? You see how there's an issue with order of priorities now. Because is 95.5 greater than or equal to 60? Of course it is. So, all right, that's the one I'm going down. That's the one it picks because that was the highest priority one. Do you see that? So you do have to be careful about your orderings and make sure it works for everybody. But I would just say put the hardest thing to do first. Like the 90 is the hardest grade to reach. Put that first and just like work your way on down the line. That ordering works out. And so that is why we need the 60 here, because we want to force all these other guys to fail in order for us to get here. Then we know it was a D, right? Then we know, all right, it wasn't anything bigger that it could have been. So I hope that makes sense. Okay. That's what I wanted to say about that. Okay. Are we good with this example? Because I have a question for you now. I want you to try if we're ready. Question? Yeah.
There's a difference between print and return.
There is, yeah. This code is not within a function. Return only is possible within a function. So it doesn't make sense to say return a character here unless I were to package this into like def calculate grade with some score or something, and then I have to indent and say score everywhere. Then I can start returning. Return only works for functions. That's a great question. Other question. Print works everywhere. It's just going to output stuff. Other questions. All right. So yeah, let me give you this one. This is an easier example of if else, so you can kind of see it more clearly. I'd like you to do something similar to that sign example, please. So here's what I want you to try. Do I want you to write it down somewhere? Sure, for fun. Let's see. You guys can show me what you're thinking. Please make sure to do that attendance, but also please go to the written ice page if you're feeling brave. I highly encourage you guys to get next to the people you're sitting next to, or get together with the people you're sitting next to. Say hello, talk about your very long weekend, and then I'd like you to go over this example together and try to come up with a function definition that works. So try to make a function. We're going to pretend like we're in the Goldilocks fairy tale and make a porridge rating function. All right. So a function called porridge rating that takes a temperature of a porridge and it gives back too hot if the temperature is bigger than 150, let's say degrees, and then it's too cold if the temperature is less than 100, and then it's just right if it's between the two. All right. Does that question make sense? So I want you to make a function similar to sine, but it works in this kind of way. All right. So you're given a temperature, and you want to give back these words with a return based on those different temperatures. Do you see the ordering that you might have to do there? So think about that. And let me know if you have questions about that. All right. Dun, dun, dun. Do I want to do that? I guess that works. You try that, and then I'll go over my example. But do you see the kind of ordering that you might have to do there? Is it okay to try A is greater than 150 first? Less than 1 means that you have to like change the order of things. Definitely try it out if you can. Go to that secret special temporary Jupyter page if you need to. I think you might be able to keep the same order. You see how that would be true? I'll give you a couple minutes to play around with it. Oh. Weird. Yeah. All right. Did you get it working? Any questions come up as you were trying it? Let's see. Oh, yeah.
So my computer died, but I was trying to take attendance, but it logged me out of the class website.
Oh, okay.
So can you just fill it in from your end for the time being?
Yeah, sure. Let me do it on this computer. Remind me your last name?
Bilal, so it's B-I-L-L.
Gotcha.
Do you need my student ID?
No, you're here now.
Okay, thank you.
All right, friends. Let's see. Yeah, let's talk about it. So I think we got it. Yeah? Dun, dun, dun. Let me confirm that I don't mess that up when I do end. But yeah, look at us. If it's bigger than 150, too hot. Otherwise, less than 100, print too cold. And then, oh, some of us know about and. That'll work too. But you could just do it with an else. Nice. Cool. I like that. So thank you both. And I promise to stop that. All right. Cool. Let's go to my example code. You could do it in that exact order, and that would work just fine. And let's talk about that. So let's see here. Let's put it in just that order, and we'll go from there. So I want to make a function called porridge rating. And it takes some temperature. I'll call that temp, maybe. And all right, based on that temperature that I was given, if it's bigger than 150, that's too hot. So if temp is bigger than 150, I'll return too hot. Yeah, can do that one. Otherwise, maybe the temperature was too cold, right? If it's less than 100, that means the temperature was too cold. Then return too cold. And then I don't know how to say the idea yet of between 100 and 150. One day I'll teach that to you. But you can actually get away with just an else right now. So just an else would actually work, and you could say just right. All right? And so this would be code that would work, and let's talk about why. Why in that else case, it really is between 100 and 150. Because it'll try this one first, right? Let's say it is between 100 and 150. If this one fails, that's the only way we ever get here, right? Is if the first two failed. So what does it mean for the first two to fail? What does it mean for it to not be greater than 150? That means it must have been less than or equal to 150. Does that make sense? For this first check to fail, for us to eventually get here, the second one also has to fail. But for the first one to fail, that means the temperature must have been less than or equal to 150. So what's the opposite of that? Opposite. We know that if we get to the next try, it must be less than or equal to 150. And that doesn't really ruin anything for the next one. It's like, all right, was it also less than 100? That's kind of the next checking that. So if it was less than 100, we'll say too cold. But if that's not true and we try this one, what also do we know? Because the first one failed, we know that it was less than or equal to 150. If the second one fails, this check, we know that the temperature was also greater than or equal to 100. Do you see that? The opposite of this one is, the opposite of less than 100 is greater than or equal to 100. And so if I hit the else, and knowing that I got there by both of these failing, what do I know is true at the same time? The number is exactly greater than or equal to 100 and less than or equal to 150. That means it's within the range. You see that? That means it's within that range. And so we'll say just right, and it will work. So this can be our else. This can be our else, and it's happy. And let me show that to you. So say porridge rating. If it's bigger than or equal to 150, like 155, it's too hot. if it is less than 100, so like even 98, 99 is too cold. But anything within the range, 100, just right. 105, just right. 150, just right. 149, just right. All the way in between, right? 125 is like the smack dab in the middle. Those are all going to be just right because all those get to here by the first two failing. If this is not true, it's less than or equal to 150. If this is also not true, it's greater than or equal to 100. Those taken together means it's right within the range I care about. Does that make sense? So the ordering is very important here because we didn't know how to formulate like both of those things at once. There's a thing called AND that'll give that to us, but maybe we didn't know that yet. So yeah, that's the secret there. And these first two don't really overlap. The order is very important if things overlap, right? Like this D check versus the A check, those did for sure overlap. But a number cannot be both greater than 150 and less than 100. So those ones don't overlap. You could have put them in any order because of that. Does that make sense? So I could have done this in this order with the two cold check first. That's totally fine because they don't step on each other's toes. That one becomes the if, and then the other one becomes the elif. That is still the same. It's still going to work. It's still going to do all the right things. Okay? Any questions about that example? Do you see it? Is that clear? So yeah, it's just like the sine function, but for free, that else gave us some power. All right? So let me show you a few examples of how far you could take this. It's kind of cool. So back to the idea of like just conditionals and some examples. Maybe I'll stick it between like porridge rating is what we wanted to do at the very end to practice. So let's do this before all that. I'll add a few extra cells. So one cool thing you can do with NFLs is like you can start making games for yourself. Like you can make a guess the number game very simply. Guess the number game. Watch. So all a guess the number game is, right, is the computer secretly thinking of a number and it doesn't tell it to you, but it gives you hints, right? So we can make a variable, secret number, we just don't ever print it out, equals np.random.choice. Give me a random number between 1 and 100. So just like I just need to give it the sequence of the numbers from 1 to 100, right? np.arange 1 to 101. So yeah, that's going to give me a random number between 1 and 100 because this is the array of all the numbers from 1 to 100. This will pick a random one out of it. And so that's my secret number, and it's different every time. So I'll print it out for fun this time. Oh, I love that it was 42 this time. I run it again, it's some other secret number, but every time we run it, we get a different secret number. So just let it run, let it think, and then we'll make us like a guess the number game function out of that. Like we'll call it guess, where n is the number that the user just guessed. And we can give them hints as to what they guess and check against the secret number variable. That becomes a game, right? So like if the number, and where n is the number that the user guesses, like you should guess 50 first, right? Guess 50. So all right, you run this cell to make the secret number and also to define the guess function. So you gave me some n number as your guess, like 50 is my n. If the number that we guessed was, I don't know, greater than the secret number, then that means they guessed too high, right? If the secret number was 50 and they guessed like 75, we'd be in this case. So we'd say too high, right? Elif, maybe their guess was too low, right? If their n was less than the secret number that we're not printing out, we'll say too low. You see how you might get there? Like you guessed, I don't know, the secret number was 75 and we just guessed 50. So that'll say too low, right? Because our 50 is less than the 75. That's true. And then otherwise, again, you see that the else kind of saves the day. If it wasn't too high, it wasn't too low, just like the porridge, it was just right. And so that means you got it. Return, you got it. So rerun the cell to play again. Do you see how that's going to work? Like, guess the secret number between 1 and 100 with random choice. And every time we make a guess, we'll run this function, right? And then it will compare against the secret number, not printing it out to us ever, until we get it, giving us hints along the way. So I just ran that. So it made a new secret number and it also defined the guess function. And so if I say guess 50, that's like the first one you're supposed to guess, right? It's like, all right, too high. So if I play this perfectly, I'm supposed to guess what? 25 next, right? Because that's in the middle of the new range. That one's too high. Guess I don't know. It's supposed to be like 12 and a half, so I don't know, 12. Too low. What's in the middle of 12 and 25? I don't know. Let's guess like 20. But eventually we'll get it. Too high. We'll guess, I don't know, 16. Cool. And so I got the secret number, and I can rerun this cell to make a new secret number and play all over again. Does that make sense? How you can use the if-else and randomness to like do something interesting? We're going to be using this for the rest of the semester. It's great. But you see how like functions and if-else's and randomness are all combining here? Do you see how like all that's working together? That's important. All right. Similarly, we can talk about gambling, because what is randomness and chances and probabilities without talking about where like the reason people invented the whole field of statistics is because they wanted to learn how to gamble better. I believe that is actually a fact. So, okay, let's talk about the game of roulette. We'll talk about this eventually, but you know what roulette is? It's this game where like there's a ball and it spins and the ball lands on a number and like you bet on the number. So that is apparently a game that people play. And here is a table of all the options for the roulette wheel that it could that the little ball could land on. So I've got a little data set in my data folder called just roulettewheel.csv, and I'll call that roulette. I do not encourage you to gamble, though. We're just going to simulate things and show you why it's a bad idea. So I can make choices, right? This is like the roulette wheel. There's a couple zeros that keep you from like having a perfect 50-50 chance, and the color is green. But the color of every other number that the wheel could land on, that your ball could land on, is like red or black. So it's red, black, or green are your options, where red and black are more numerous. There's just two greens. So you can simulate, right, you playing your roulette and like spinning the wheel and figuring out which color it lands on by randomly picking one of these colors, right? These are all the options with as much frequency as necessary for all those options. If I take this column, I get the array of it, right? I get all the arrays of all those colors. I can np.random.choice from that. You see it? That's me spinning the wheel. That's me spinning that wheel. So let me show that to you. Boop. So I can say, hey, give me roulette.column called color, or it's column index 1, right? 0 is the pocket, color is index 1. So that's like every color on the roulette wheel. I can simulate a spinning of it and figure out which one the ball landed on by saying np.random.choice from that column, from that array. So I'm randomly spinning the wheel, and we get black. So if you bet it on black just now, you won money. Okay, so a valid I want to simulate this, and so one strategy for playing roulette is always bet the same color, like always bet black, always bet red. Let's bet red because that's what your book does, and I'll show that to you as an example. All right, so we're simulating something right now. Let's simulate us making one bet on red for an amount of money, where the amount of money is something we're giving to this function. So apparently the way that you play roulette is if you bet $5 on red and it lands on red, you keep your original $5 and you also gain $5 more. You gain what you bet. If you bet on red and it was something other than red, it was like black or green, then you lose your $5. So your net profit is negative $5. But if it landed on red, your net profit was positive $5. So it's that amount you get either back or you lose it. All right. So I want to simulate making one bet on red for a certain amount and seeing how much money we made. Okay. So if we go to a casino, so here's us spinning the wheel randomly. Right? And we're betting red. So the color that we get back, let's put that in the color variable, could have been red or black or green in color. And if it was red, we win our bet, right? If color was red, we get that back. We get that. And if color was red, then I want to, what does that mean? That means we won our bet. If we bet $5, we get $5 more back. So our net profit is whatever that amount was, AMT. If we bet on red and it wasn't red, that's the else case, right? Otherwise, if it wasn't actually red, then what is our net profit? It's negative amount in dollars. We just lost the money that we used to bet with. So you can say negative amount, or you can say amount times -1. But like that is us simulating a bet on red and how much money we made. Does that make any sense? I don't know gambling very well, but that's apparently how the game works. So one bet on red, let's say we're always going to bet $1 on red. So if I run that, it looks like I just lost, okay? And so I can do this a few times. I can say I'll bet $1 on red a few times and show me the outcomes, my net profit with commas in between. So it looks like I just broke even for this simulated version of the game, which is probably what would happen in real life. So you keep betting $1 on red. The first time I lose $1. The next time I gain $1 because it was on red. The next time it was also on red. I gained $1. The time after that, it was something else. It was green or black, and I lost $1. So I walk away having gained or lost nothing, which is kind of nice, I guess. Keep betting $1 on red. You can stay there for a while until you get a bunch of greens. So yeah, that's kind of how that works. And you could play the same game for like simulating other like casino games, because legitimately that's why statistics was invented, to try to formalize what happens when you gamble. So same idea for like dice. It's like, what is a die? What is a die? Because that's the singular version of dice, right? What is a die? But just as like a thing that you could roll that has, so like a normal die has 1 through 6 on it, right? So what are my options? 1 through 6. How do I generate that? I just need an array of 1 through 6. So give me a range 1, 7. There's numbers from 1 to 6. So simulating me rolling a die is just np.random.choice from that. Yeah? So that's a die roll. And so I get a 4, apparently, for that. You run it again, you get a different number, right? I randomly got another 4. So that's the thing. Does that make enough sense? Questions about using like random.choice to do simulations. And you could use tables for that too, because you could just like get that column out, choose from it randomly. That's what we just did. And then you can like do some simulations as well. Like, all right, if I keep betting on red, how much money do I make? You're eventually going to lose all your money. And I will simulate that before the end of class. All right. I think that's what I wanted to say. And then our porridge rating example hopefully makes even more sense now why we do that in that way. But yeah, that is conditionals and some randomness stuff. Are there any questions before I move on to another topic that includes all these things, of course? Are we ready for it? So I want to teach you something else that looks like conditionals, but it doesn't just run the bodies one time, it maybe runs them multiple times. And that's called a loop. So I want to teach us something called a loop now. If we're ready, sounds like we are. So a loop, the loop that I want to teach you is called a for loop. There's two different main kinds of loops in Python. There's one also called a while loop, but I just want to teach you a for loop in this class, really. So a for loop, what it does is it goes through a sequence, which is usually our sequences in this class are arrays. So a for loop, we say it goes through a sequence, and of course we want to be fancy and pedantic or snooty, maybe. We use the Latin, a word with a Latin root coming from to go, iterate, like itinerary, that comes from the Latin root to go. So iterate just means to go through something. So I say that this for loop that I'm about to teach you, it's going to run code. It's going to iterate through something. It's going to iterate through a sequence of numbers, maybe. So a for loop is something that repeats. So the word loop just means it loops back around on itself. So this is going to be code that repeats itself. All right. So that saves us from having to copy and paste a bunch of code. If we have it come back to itself, that's kind of nice. So yeah, we say that a for loop iterates through a sequence of things. And this is kind of how you use it. You say the word for, then you give a variable name, and then you say what you want to go through. In what? You say for some variable name, you say in, and then you give the thing you would like to iterate through, the thing you'd like to go through and look at. So np.arange 1 to 11, that is going to generate the sequence of all the numbers from 1 to 10, right? That'll give me the array from 1 to 10. So that's the sequence you want to go through. You put that there after the in. That's supposed to be an arrow. This is the sequence you want to go through. And the way it's going to work is You also say colon, and then you give a body. And the magic is that the body gets to use that variable name that you say there. What happens is this I gets a chance at being every single element of that sequence, from 1 to 10 in this case. So I gets to be 1, then 2, then 3, and it's going to run this code, the body of your for loop. It's still called the body. It's going to run that with I, this I variable, whatever you call it. It could have been X, whatever you want to call it. It's going to run it with I set to each value in that sequence one at a time. So the very first, that gets a chance at being everybody. So the very first time this code runs, this loop runs, it's going to run this body 10 times because there's 10 things in the sequence. All right. So I is a variable that gets made, and it gets a chance at being everybody in the sequence. The very first time, it's going to be the 1, right? Because that's the first element in the sequence. So I gets to be 1 at the start. And then we say print I. We say what we want to do with each of those values in turn. So this is a loop that's going to print the numbers from 1 to 10 in order. Does that kind of make sense what it's about to do? Because I gets a chance at being 1, of course. And so we say print I. It will print the 1 to the screen, if that's the screen over there. Then, make it a little bit smaller. And then I gets a chance at being the next element of the sequence. The next one is 2, right? So I gets to be 2, and it's also going to run the code, the same code, with I being 2 now. So that variable gets to range over, we say, that sequence. All right, so the variable name gets, every time it runs, that new variable name that we put here, whatever we call it, gets set to the next thing in the range that we supply there. And then the body will run with that thing now. So I is 2, we run print I with I being 2, so it'll print 2. And then now I gets to be the next thing in the sequence. It's just going to keep running that code for as many things as there are in the sequence, and I is the variable name that we chose to use for each value that the sequence takes on. So I is now 3, we'll print 3. I is now 4, we run the body where I is 4, so printing I means print 4, all the way down to 10, right? I gets to be the last thing. We print it all the way to 9. The last thing in the sequence is 10. We'll run the body with I being 10 one last time, which prints 10, and then that's the end of the for loop. So it just goes through, lets this variable be everybody in this sequence, and it runs whatever code you want to put here. It could have a bunch of lines if you wanted to. It will run all that code with the that variable taking on each value of the sequence in turn from left to right. All right, so that code's going to print from 1 to 10, and I hope you see why. All right, so let's go from there. Let me put that up here so we can watch it work, and then I'll ask you if you have questions. So yeah, so remember, I want to go through something. For loops, they iterate through, they go through a sequence of things. So you need to start with a sequence somehow. You can get it from a table, you can generate it yourself with a range. So here is me generating the numbers from 1 to 10, right? A range 1 to 11. If I want to go through the sequence and do something once, the same thing once for each value, I can use a for loop. I can say for I in np.arange 1 to 11. And then I say, what do I want to do with I? Because I is going to take on the value of that of each element of the sequence in order. I just say I want to print I. All right. So I gets to be 1, then 2, then 3, all the way to 10 because that's the last element here. And then it's happy. So when I run this code, I see the numbers from 1 to 10 printed to my screen in that order. Does it make sense why it's doing that? Is that clear enough? Yell at me if you have questions. What can I do to make it clearer? You kind of see what's going to happen. These variable names could change, of course. You could have said for x, and then just use x. X is the variable name that gets set to all these things. Still works. Still does the same exact thing. I just use I because I'm iterating through things. I for iteration, kind of. So there's that. You can do this all day long. Is there a question? Yeah. Oh, you want to print the index as well? Is that what you're saying? Oh, nice. That's a great question. If you wanted to print the index too, you'd unfortunately have to play some games of making another variable. That's the easiest way. There's something called also, there's a function called enumerate that also gives you the index next to it, but I don't want to teach that. You could look that up if you like. There's a function called enumerate that works for this in Python that also gives you the index, but probably the standard way, the easier way conceptually would be like, what index am I at right now? Or at 0 at the beginning. So you print the index as well as the value, and then index equals index plus 1 to get ready for the next round. See how that's going to print that in that way? That that's the simplest way to probably do it. You just have another helper variable and you change it yourself as it goes along. But there's also that enumerate that would do it as well, if you want to look that up. That's a good question. Other questions? And that's what you want to write the index next to it? Yeah. So that would be, okay, yeah, I think I understand what you want. The way to do it in a C++ style way would be you let I range over the indices rather than the values. This one's ranging over the values of this sequence. But let's say we had a sequence, let's call it SEQ for sequence. Let's do np.arange. I like this idea. Arange, let's do like from, I don't know, from 50 to 100. So now it's not just from like starting at 1 or something. Like let's say I want to print out all these values of this sequence from 50 to 100, or let's do like 50 to 75 to make it easier. So let's say I want to print all these values in this sequence array. I need to ask myself, what are the valid indices of this array? If I want the indices too, what are the valid indices? It's all the way up to, it's from 0 up to the size of it minus 1, right? So the length is the function that we use to get the size. So it's up to 25. That's 26 minus 1, right? So I can say np.arange just with the length, and that will give me all of the valid indices for this sequence. Does that make sense? Because arange with just one thing starts at 0, and it goes up to but not including that thing. So this is the array of all of the correct indices. And then I can say for I in all these guys, print sequence dot item I. That would be like overkill for what we need because we're just looking at the values. But this is you going and ranging over the indices and going to each index. Does that make sense? Yeah, that would be like kind of the C++ style way of using this. Is that what you really wanted? Yeah. Yeah, that's a good question. That would be the way to do it. But if you just want the values in order, just go like this. Okay. Other questions? All right. This is like the indices. That's a good question. All right. Let's see. You can make any sequence. It doesn't have to be numbers. You can be like, for every, let's make an array of people. We can do me. We can do my cat, Lonzo. We can do the other computer science professor, Bill. So there's an array of 3 people. And I can be like, for every person in this sequence, in this array, print that person. I don't know, print person, and then it goes through them. Or you can do something with each value, right? Person times 3. You can multiply strings by numbers, surprisingly, and it just duplicates the string. So you kind of see what's happening there. Person is a variable that's ranging through each of these values of this sequence, and then this is what I want to do to each of them. I want to run that code, please. That's what we're asking of Python. You see it? Yeah, it doesn't just have to be numbers. Yeah. So cool. Let's go there. So I have another question for you now. Here's the code to print from 1 to 10. Can you change that to make code that prints from 5 to 50 by 5s? 5, then 10, then 15, then 20. You see how you need to change that? So give that a try. If you'd like, put it on the written nice page. I'll clear that out. You can refresh the page if you're already on it. But try to change this code to print from 5 to 50, including the 5 and including the 50, but going by 5s. You see what you need to do? You want to do it this way? I guess you could do a bunch of weird stuff. You could I'll show you later. Because technically you could change a couple different things in this code. You can change the first line and it would work, or you can change the second line in a weird way and it would work, couldn't you? Or not in a weird way, just like in a different kind of way. But take a few minutes to try that out. Just remember what arange does, etc. And you don't have to say I if you don't like I. Just like call it X. It's the thing you're going through, that's its name. The thing that comes after 4. Another few seconds to try it. Let me know if you have questions. Amazing. Can I stop it before it makes sound? Yes, I can. All right. I think there's a couple ways to do this. The way that sticks out to me would probably change the A range. Yeah. The secret third option to A range is your increment. That would work. Is that what we chose? Yeah. Nice. That would probably be the way that I would think to do it. But you could also keep going. You could also keep going from 1 to 10, right? Keep going from 1 to 10. Just like instead of printing the 1, multiply the I by 5. You see that? Because then we'll print I 5 first. Then 2 would make it 10, and all the way up to 10 would make it 50. So you can change either this A range part or the I part. Just change it to I times 5. See that? That's pretty interesting. We have options as programmers, don't we? Let's go back to here. Boop. Well, let's do that. So you'd be like I times 5. So like this was the original one, prints from 1 to 10. You'd be like I times 5, prints from 5 to 50. Or keep it printing I and change it to start at 5, go to, I don't know, not 50 is not what you put here. You put like 51 or something, and then you can go by 5s. Yeah? That would also work. Those are your 2 options. And either way is valid. It depends on what you're trying to do, which way makes more sense to your brain. So I think either one is perfect for this example. Yeah, questions about that? Because honestly, that's more or less everything we need. That gives us so much power. Just everything we just learned gives us ridiculous amounts of power. And I like to show that to you now if we're ready. So we'll end on this slide. I'll give you a question to try next time. But using loops to do things a bunch of times and randomness to like do simulations, right? To like, all right, flip this coin, see what the answer was this time. You can do that millions of times and like keep track of values inside of your loops. So you can use loops plus randomness to like simulate you playing roulette 1,000,000 times with $1 million. Isn't that cool? You could simulate flipping a coin. Like, all right, how many heads do you get usually? Try it out. So I want to, and then we can make pretty graphs from all that. And like, this is just so satisfying what I'm about to do because it combines all the things we've been learning to make simulations of things. And that is where we're going next in the class. So let's learn how to make simulations. I hope you can kind of see, we already did it for like roulette. We played it once, but you can make a loop now to play roulette a bunch of times. Yeah, that's where we're going. So, dun, dun, dun. You know that I can say 1 bet on red, right? Where I made that function to play roulette once, and the amount that I bet was $1. I either gain $1 or lose $1 in that case. So there's my one bet on red with $1. I won this time. I won again. I should probably go home. But no, I stay and then I lose. So, okay. We can do this a bunch of times, right? If I want to do it a bunch of times, I can say for I in np.a range 10. This is just a little sequence from 0 to 9, right? But I'm not going to actually use I just kind of want to run this 10 times. Because it's not the last thing anymore, I have to say print to show the answer that it gives back. Because this is not like the real last line anymore because it keeps getting run. So I have to say this for a for loop to get it to output things. But I hope you can kind of see what's about to happen. Do you see how it calls one bet on red 10 times and it prints out the results? Like how much money I won. I won -1 the first time, -$1 the second time. Like I lost money the first 4 times, but I made a little bit of money. But I lost more money than I made for this 10 plays of the roulette wheel. If I play it again, it looks like I again lost more money than I made. That is the hint. That is always true. The house always wins. So, okay. Notice, do you see how this loop is working? I'm essentially saying for I in np.a range 10 so that I can run this line 10 times. I'm not actually talking about I in the body of this loop, am I? I'm not really using it. I'm just using it, this loop, to control how many times this line is run. Like I don't care that I is going from 0 to 9 because that's what's happening. I'm not using I. I'm just using it to do something 10 times. You see that? So that's a philosophical thing, I guess. So I'm not using I here. I just want to have something happen 10 times. I'm not using I here. The loop just makes sure that I'm running the body 10 times. That's me enforcing that. If I change this to 100, now I'm running it 100 times. That's an easy way to control how many times the body is run, even though I'm not using I. Okay? So that's my loop. And now interesting things can happen. We can keep track of how much money we make. Okay? Watch. We can keep track of our winnings, right? Winnings equals $0 at the start. And then I can say 100 times for I in np.a range 100. I will go from 0 to 99. So 100 times it's going to run the body right now. I can say like winnings equals whatever it was plus play again. Another bet on red with $1. See what's going to happen here? It's going to accumulate in that winnings variable how much money I've won. So this code is updating 100 times, right? Updating the winnings variable. And we say accumulating. It's accumulating a value. Accumulating the sum of our winnings. It'll almost certainly be negative every time. So this is, do you see how it's essentially like this code, this loop, it's really just kind of copying and pasting this line 100 times. That's essentially what's happening. It's just much cleaner to do it this way, right? I'm not using I, I'm just making sure, I'm using this loop to make sure that I run this line 100 times, which means I'm playing the game 100 times and always updating and keeping track of how much money I've won or lost. Does that make sense? Questions about that? So I want to print the winnings at the very end after I do that. So it's very quick to the computer to play 100 games. It looks like this time I won $2. I walked away with $2 after betting on red 100 times. You see how that's working? I won $2 this time, but usually you will not win very often. Okay, this time I won $10, but a lot of the times you'll win $0, -$, right? You walk away having lost money. Yeah? Isn't that cool? So this might be a little confusing. Winnings equals winnings plus something. Just remember what's going on there. The way it's working is like, say x was 42. X equals x plus 1. That's making it 43. Does that make sense? Like it's first doing this side and then shoving the answer back into x. So that's going to make x 43, make it bigger. So this is just adding into winnings whatever we just found right here. Okay? There's actually shorthand to this x equals x plus 1 thing. If you're coming from another language, you might be familiar with it already. It's called the plus equals. So instead of this line, x equals x plus 1, that's just so common in Python that people say x instead. Plus equals 1 is a syntax that you can use. So x plus equals 1, that's equivalent. Equivalent. to the above, it's also going to add in 1 to the variable x. Does that kind of make sense? So now x is going to be 44 because this is 42. This makes it 43. This code is equivalent to the other code, so it's going to run again. X equals x plus 1, and so that makes it 44. Okay? So you have options now. I could have said winnings plus equals 1 bet on red with 1. Okay? But we've just simulated playing a game a bunch of times. That's pretty powerful. We can make graphs from this. Like, there's a lot of cool things that can happen now. And I want to show that to you. The way that we get there is we need to keep track of things by building up a sequence. Let me show that and how that works. We need to be able to add to the end of a sequence right now. All right? And so that is, luckily enough, we np.randomChoice and np.count non-zero. Right after that, there's np.append. This extends a sequence, it extends an array. If you say np.append, give it your starting array and give it another value to tack onto it, and it's going to give you back one bigger array with the old array plus the new item at the end. That's what it's going to do. So like here, if this is your array, then if you append to it 1000, it's going to take what was there and add the 1000 and give that back to you. Okay? So append extends your array with a new value. And that's how we can keep track of a bunch of stuff. So that's the last thing I want to show you, really. So if I have an array, which is 1, 2, 3, my array is just 1, 2, 3. If I say np.append with a and 4, that's going to give back the array 1, 2, 3, 4. It takes what was in a and it adds the 4 at the end. See that? This, like a lot of other things in our libraries, that doesn't actually change the original sequence A. So A is still 1, 2, 3. This just gives me back a new array that has been extended. Usually you want to make that called array A now too. So a common pattern is don't just do this, but like set it back into A. Then A really does become the array 1, 2, 3, 4 after that. Does that make sense? Set it back in. Like set it to that, and then also set A to be the result of adding 5 to itself. This is just like, it's a little weird in what it's doing, but this is going to force a 4 and a 5 at the end of A itself. Like this will create the array 1, 2, 3, 4, put it back into A. Now A is 1, 2, 3, 4. So this will make 1, 2, 3, 4, 5. Put that back into A. Now A is 1, 2, 3, 4, 5. You see what's happening? So A really holds that now. I've extended it and put back into the name A. All those things. Okay? If we do this, we can make a better loop here. We can actually keep track of like, all right, which games were the winning ones and which ones were the non-winning ones. We can keep track of every time we won $1 and every time we didn't win $1. Every time we lost $1, because those are our two options. So instead of just keeping track of the sum, we can keep track of every winning, every game that we played. So instead of doing it this way, let's do it with the appending way. Let's say winnings starts out as an empty array. Make an array with nothing in it. Yeah? Make an array with nothing in it. And then I can say each time winnings equals np.append the old winnings to this new play of the game. Yeah? Do you see what's going to happen to winnings now? It's going to be extended. The first time it's adding one element and there's one thing in it. Then the next round it adds a second element, all the way to 100 elements. And this is more data. It's better data now because we're keeping track of, we now know that the first time we played the game, we won $1. The second time we played, we won $1. The third time is the first time we lost. Like that, we have more data here rather than just the sum of it all. Does that make sense? Because you could play the same game. You could now ask, all right, what's the sum of our winnings and get back what we had before. But you can also do more things, right? Because you can ask for what is our average winnings, np.average over winnings. You can do more math now. On average, we're losing 8 cents every time we play the game for this run of the game, for this run of 100 games. Does that make sense? Now you can shove this into a table now. You can do a lot of really cool stuff. So let's do that. So we can say, all right, here are our outcomes of playing our game 100 times. You can say that's a table, a blank table with a new column called, let's call it winnings. And let's have it hold all these values, these ones and negative ones from here. That can be our column. So now I've made this 100-long table with ones and negative ones, which is kind of ugly. But I can make graphs from this now because tables know how to make graphs, right? I can make graphs. I can do counting very easily, right? I can say like outcomes dot group now. I can group by the winnings column. That's the only column anyway. And that by default counts. So it shows us that we lost 54 times and we won 46 times. It's very useful, right? we're doing some data analysis very cleanly, but after doing a simulation, right? Just by virtue of keeping track of each value with an array of things with this np.append, rather than like getting just the sum like we did here. That's more powerful this way. You can you can still get the sum, that's for sure, but you can also put it in a table, group by things to see things quickly. You could, after you've grouped, right, you can do 1 and -1. You can treat them like categorical ideas, and you can do a bar chart to show like, all right, relatively within a picture, oops, I have to say winnings, in picture form, all right, how many times did I get -1? How many times did I get +1? Here's the count. You can see it graphically now. Like, you get so much power. So much power. It's wonderful. Does that make sense, how we got to this? It's so nice. All right. So for my last trick, I just want to go over, let's do coin flipping now. That's more fun. We know how to flip coins more easily than how to play roulette, probably. So let's go back to the idea of coin flipping. At the very start of class, right, I made this array called coin that just holds our heads and tails. So coin still exists. Coin is an array that holds just heads and tails, and I can pick from it by doing np.random.choice, right? I'm going to say np.random.choice from coin 100 times. This flips a coin 100 times, right? Let's call those are the outcomes of my experiment, we say. I can count how many heads there were by saying, like, take outcomes, check how many, like, were they equal to heads, right? And this gives me trues and falses, true if it was heads, false if it wasn't. And then I can np.count non-zero, how many times it was true, right? This tells me how many heads there were in this run of the coin flipping game of 100. That's my num heads, maybe. If I rerun it, it's going to flip another random bunch of coins. This time there were 57 heads. Okay? You see how I'm getting that? np.random.choice stuff? That's pretty neat. So now we can turn this into a function, right? We can, just like our one bet on red, we can do def flip 100 coins and count how many heads there were and count heads. Very long function name, who cares? You can do the same game, right? This is what we want to do every time we call this function. It's one simulation of flipping 100 coins, right? Return, we just return back the number of heads now. And so now I've got a function that I can just call, and it flips 100 coins and counts heads. How many heads we got? Gives me back how many heads. This time we didn't get a lot of heads, unfortunately. Okay? And now we can run this just like we did this before, right? For one bet on red. We can now flip 100 coins and count the number of heads a bunch of times and see, like, all right, usually I expect to see 50 heads. That won't happen every time. It's probably the most popular thing to do, though. Let's see that in a graph form, all right? So this is really, really cool what we can do now. We can be like, all right, for I in np.arange, like 20,000 times, if you want to. We can keep track of how many heads we get every time we flip 100 coins. We can play this, we can run this function 20,000 times very quickly inside of the computer. And we can see the scores, all right? So what I like to do is keep track of all the time, all the numbers of heads I've seen. These are like the head counts, I guess. Started as an empty array. And then now 20,000 times do the following. Flip 100 coins and count the heads this one time, right? 20,000 times I want to do this. Flip 100 coins, count heads, and remember how many heads I got each of those 20,000 times. And this is a new head count. Put it at the end of head counts. np.append to head counts. This new head count of flipping 100 coins again and counting how many heads. So head counts equals that. And sometimes, like, you want to control this easily. Like, you can see it's 20,000 times, but we can call this something. We can put this somewhere else. Sometimes you'll see this in your books, like, how many repetitions of my simulation do I want to do right now? So num repetitions equals 20,000. And it's like for I and np.arange num repetitions. This is going to run this code num repetitions time, whatever you put here, and you can control that yourself. Okay? So like we can make that happen. Is it clear what's about to happen when I run this cell? 20,000 times, it's going to call this function. So it's going to simulate flipping 100 coins and counting how many heads the first time, the second time, the 20,000th time. It's going to flip really how many coins? 2 million coins, right? In total, something like that. So 20,000 times it's going to flip 100 coins and count the heads. It's going to play that game out 20,000 times, and it will keep track of all the head counts, all the counts of all those heads that I've ever seen. It happened in the blink of an eye because computers are cool. We can confirm this. What does my head counts array look like? It's got 20,000 things in it. You can try to print it out. It won't show it all to you, of course, but it's 20,000 things. The first time we flipped 100 coins and counted the heads, we had 46 of them. The second time we flipped 100 coins and counted the heads, we had 49 of them. The 20,000th time we flipped 100 coins and counted the heads, there were 48 of them. Does that make sense? That's what we got. And we can make a table of this. Make a table of this, we can see what happened, and we can go from there. So here, let's make a table with some columns. The normal one to put is like the number of heads, right? And that's just all of our head counts. Make that a column. But we can also keep track of like which version of our game was this, which repetition in our simulation. We can say repetition. Because we want the first one to be repetition number 1, the second one to be repetition number 2. And so I can make np.arange here. What's the sequence I want to get back? I want to make the numbers from 1 to 2000. 1 up to num repetitions, really, plus 1. Oops, I pressed a button. Plus 1. This will make the sequence from 1 to 2000, and it will match over with the head counts each time. So let's call this results. So like 1, it was 46 the first time. Repetition number 2 was 49. All the way to repetition 2000, or 20,000, it was 48. So does it make sense how I made this table? Because now we can make pretty graphs. All right, so like if it's a truly random coin, and that's what we're simulating, right? We're simulating true randomness. It's not a loaded coin. It's not an unfair coin. We are really doing something perfectly randomly every time we say np.random.choice. We should expect to, if we're flipping 100 coins, we should expect to usually get 50, right? It's not always 50, but when you keep doing it, more likely you're getting numbers close to 50 or 50 exactly, right? So 42 is kind of close enough. It's never going to be perfect always, but we can keep track of like how many times did we see different numbers. And we'll see a pretty graph, all right? So I can say results. I can say .hist to make a histogram, right? On the number of heads. I want to see the distribution of the number of heads because I flipped a bunch of coins 100 times. It's going to be a distribution that looks like this. You can see that it's kind of like from 35 to like 70-ish. So maybe like 30 to 70 that we can do. So let's change the bins. We can be like the bins equals np.arange. And a cool thing that we can do to like center them properly is to make, because we know these numbers are always going to be whole numbers. So we can say we can do it by 0.5. So like 29.5 up to like 70.5. So 70.6 by ones. And then these values are going to be centered like around 50. So the 50 bar is really from 49.5 to 50.5, and it's going to hold the number 50, like how many times we saw 50. So that's why we go by 5, so it centers these values properly, if that makes sense. But now we can see that, yeah, if you flip 100 coins and count how many heads you got, usually you're going to get about 50 of them, all right? So that's the most popular thing that happened when we did this 20,000 times. But it's not necessarily the case that you're always going to get exactly 50. We saw that already, right? You can get 42. That's just fine. But it's less likely. That leads into the idea of probability. That's where we're going. It's very fun. And this is a very pretty graph. It's called a bell curve, right? Maybe you've heard that before. It's centered around 50, and it tapers off in a clean way that maybe you've seen in a statistics class. It's really, really nice. And you can do math on this, but does it make sense how I made this graph and how you can interpret it? This is like the results of all of our simulations. All right, so you can also do like These were our head counts, right? It shows you that 50 is like smack dab in the middle of all of our head counts. That was the normal thing that we expected to see most often. That was like the highest bar, where it's tapering off on both sides at like the same rate. It's less likely to get like 40 heads, just as not very likely to get 60 heads when you're flipping 100 fair coins, but it's still possible. It's not really possible to get 70 heads or 30 heads very often, but you can imagine if you do it enough times, billions of times, you'll eventually get all 100 heads, right? It's just very unlikely. So that's a probability problem. But we can kind of see this idea that 50 was in the middle by taking the average, np.average of all these head counts. It really was trying to center around 50. We got a few bits more under 50 than over 50 because we got this number back, but more or less it was about 50. And yeah, it's never perfect, but on average, we saw 50 heads when we flipped 100 coins. And that's a simulation. And that's where I wanted to end. Are there any questions about that? How we got here? A lot of stuff, but I hope you see how it all fits together and how it's going to make our lives easier and more exciting in this class. And that, if we're good, is where I want to leave us. Any last questions that we want on the recording? Because this is where I want to come back. We'll do some more simulations because we have a lot of power now. It's very, very cool. To be continued. That. So yeah, if we're good, let me make this blue because I apparently decided that to be continued slides are going to be blue. And remind you of things. We've got nothing new coming out this week, just the one lecture because of the holiday. And yeah, do remember that eventually we are going to have a midterm in this class. I think I promised it around week 9. So I'll talk about that next week though. Okay. But yeah, that's all that I've got for us for the day.